We are here to introduce our work towards feasible dynamic grasping, leveraging Gaussian Process Distance Fields, Equivariance, and Riemannian Mixture Models. Grasping objects may seem like a simple task, but dynamic grasping remains challenging. This challenge arises from the diversity of object shapes and the kinematic constraints of robots, as well as potential collisions. To address these challenges, we propose a sequential modular pipeline that provides direct or potential solutions. Neural networks are a common method for object grasping, but they have trouble adapting to new environments. Hence, researchers have explored methods like neural grasp distance fields and SE3 diffusion methods. These learn grasp cost functions that can incorporate factors like collision avoidance and manipulability. But the implicit nature of these methods makes it difficult to add other constraints, such as object affordances. Therefore, the question we want to address is, how can we create a cost function for grasp poses without relying on implicit learning? This is our pipeline for dynamic object grasping. In the first half of the pipeline, we sample grasp poses from a partial point cloud of an object. Then we do reactive grasping using the object's pose information. We will go through the details of the pipeline one by one. To handle partial views, we utilize the Gaussian Process Distance Field, GPDF. It models the occupancy of a query point based on point cloud observations using a specific kernel function. We measure the distance of a query point to an object using the kernel function's inverse. Unlike the original method, we refine this distance prediction with an iterative algorithm. The GPDF is capable of reshaping point clouds, estimating unseen areas, and measuring surface uncertainty, as depicted in the images on the right. Using the GPDF, we perform SE3 equivariant grasp sampling with vector neurons on a centered point cloud. Two small point net architectures with vector neurons generate both SO3, equivariant, and invariant features, speeding up training and simplifying inference by avoiding extensive data augmentation. We then filter grasp poses using force closure analysis and use pre-trained Riemannian GMM-based reachability, which models the SE3 reachable workspace to ensure the poses are within the robot's reach. Custom filtering methods can be added to further enhance the grasp pose selection if needed. The key challenge in subsequent steps is converting discrete grasp samples into a cost function or a field to guide the robot towards optimal grasps without explicit grasp selection. Therefore, we create a target set instead of a single point, using either task space or joint space methods. The task space method fits a Riemannian GMM to grasp poses, forming a probability distribution. With the Riemannian Gaussian distribution defined, we create a Riemannian GMM and its gradient. Utilizing gradient ascent on this distribution helps identify likely optimal grasp poses. Iterative refinement produces a vector field, guiding the robot's end effector toward optimal grasps using inverse kinematics. Additionally, we provide a joint space method for scenarios where optimal end effector poses don't align with preferred joint configurations. We sample multiple inverse kinematics IK solutions for each grasp pose and create a smooth joint pose distance field using GPDF. This leverages the fast IK flow neural network to efficiently generate IK samples. For 2D examples, the target sets form a heart-shaped task space, and our goal is to create a smooth joint distance field that captures these IK solutions, allowing the robot to be guided to any point on the shape by following the gradient. For experiment results, we assess the effectiveness of our pipeline in both simulated and real-world settings. Our task space method outperformed the SE3 diffusion field approach in both static and dynamic object grasping. It was faster and smoother, but occasionally had issues with joint limits. The joint space method had better joint-related attributes, but was slower and sometimes exhibited larger, less predictable motions, which could be challenging for human-robot interaction. Therefore, the choice between the methods depends on the specific task requirements. In conclusion, this work introduces a new approach to dynamically grasping different-shaped objects. It shows how Gaussian process can be used for object shape completion and grasp filter. The work also demonstrates using Riemannian manifolds with GMM to analyze the reachability of grasp poses. At core, instead of selecting specific grasp positions, this work shows two methods for creating grasp fields, in task space and joint space, which offer different strengths in terms of speed and handling complex scenarios. The challenge for this work lies in efficiently getting a large number of samples and learning the continuous field in an online manner. In the future, we aim to improve these capability and relax assumptions, such as requiring object pose knowledge. Overall, this work provides ideas and techniques that could enhance the reliability and adaptability of robotic manipulation in a plug-in and out manner. Thank you for listening.